Thank you. Last talk of the whole conference, so thank you all for still being here and still hearing me out. So thanks to the talk of this morning, I can just quickly go through the introduction of my talk and motivate the modeling. And I think the answer to this particular question is yes, as we've seen plenty of evidence early on today and the past few days. So yeah, I just want to present the results of our model to reproduce QPEs in the 4 sources that we knew at the time when we wrote this paper. And I did this work in collaboration with the whole Milan group and also some of the QPE experts such as Giovanni, Margherita, and Riccardo is in the audience. I trust that every one of you by now knows what is a QPE. So, I mean, I would just quickly highlight the few properties that are relevant. So these are fast bursts in soft X-ray, thermal spectra. They have different recurrence time, but between 1 to a few hours or tens of hours at most. And their peak luminosity is 10 to the 42 to 10 to the 43 years per second, and they've been detected by all the X-ray facilities. So this is GSN. Again, you've seen it multiple times. The only thing that I want to highlight here is that since the X-ray light curve follows pretty well the T to the 4 power dependence on this temperature, then the bolometric correction is small. And so this was the first indication, or among the first few indications of the fact that the disk in these sources is narrow. So, and this points towards the direction that it is a TDE-driven disk. Otherwise, you would see optical and UV emission from the outer parts of the disk. The other interesting thing, and I'll come back to it later, is that QPEs appear only in low luminosity states of these sources. So this is a property not only of GSN 069, but also of other sources. And these are just the newer detected QPEs by Giovanni on the same source. So the let's say Embry disk impact model was initially actually proposed by Shan et al. In 2021. They assume that the disk is an AGN disk, though, and I think that the mechanism that they proposed for the emission was related to shocks in the disk by the companion. And then, so this model was essentially developed even more by Itai and Brian and by ourselves, and also by later on by Takawa, as Itai has shown you. In a week, there's been 3 similar papers, all proposing the same model. So what we did was to construct the evolution of an Embry with a rigidly precessing accretion disk. So since we already had a code that evolves the Embry orbit with 3.5 post-Newtonian corrections, which include all the relevant precessions that you want to include in this model, we just added the rigidly precessing disk, assuming that this is a TDE-driven disk, so it's rather compact and rather thick, geometrically thick, so that it can precess as a solid body with a frequency which is essentially a weighted average of the lens steering frequencies at each annulus in the disk. So these are, so we went back to my very old paper now on the rigid precession of TDE-like disks. And so you can see that it is a function of the spin of the black hole. We include also retrograde orbits. The periods that you expect are between 1 to 100 days for a 10 to the 6 solar masses black hole. They are even longer for a 10 to the 5 and so on. And the dependence on the disk mass is given by the fact that the lower the mass of the disk, the more radially extended is the disk, and so the slower it precesses. So we assume that the impact between this precessing disk and the Embry companion produces the QPE. Since we wanted to eventually construct the light curves, so not only giving timing properties, but also actually build a light curve that is similar to the observed ones, we had to assume an emission mechanism. And so, I guess the original idea of this mechanism is from Fiaiochi in 2016. This has been, of course, developed more by Itai and Brian. And essentially, every time the companion crosses the disk, there are two, let's say, clouds of material that are expelled from both sides of the disk. And so if you assume that as we do, that the companion is a black hole, then you have to calculate the influence radius to understand how much material is shocked. And this is inversely proportional to the relative velocity between the object and the disk, and is proportional to the mass of the secondary black hole. And this has to be of the order of 10 to 11 centimeters in order to be able to produce the luminosities that we see. So we assume that the initial size of the cloud is exactly the influence radius of the companion, and then that the cloud expands adiabatically by a factor of 3 in the lifetime of the QPE. So we tune this expansion, let's say, specifically to every source, because every source has its own timing properties, and so we just change this delta T QPE to adapt it to each source. Then the gas in the cloud is shocked, so it goes from an initial temperature, which is the temperature of the disk at the location of the impact, to a final temperature, which is given by this relation in a radiation pressure dominated gas. So the cloud emits initially in the X-rays, and then as the cloud expands and cools down, the emission transits to the UV, and you don't see it in the X-rays anymore, and the QPE is gone. So we calculate the luminosity of the cloud, assuming that its size changes with time, and this gives us the sudden rise and the slow decay with time of the flare. And then we just assume a black body emission, and this expansion temperature is related, of course, to the post-shock temperature of the gas, which is of the order of 10 to the 6 Kelvin, so in the soft X-ray. And then, as I said, the cloud temperature decreases as the cloud expands, and so the QPE ceases to exist. So the factor 3 expansion is supported by this folded QPE profile of GSN 069, although we have seen that in other sources you get this, more or less the same factor of expansion. So you can see here that during the rise, the black body radius is around 4, and then it goes all the way up to 12 by the end of the flare. And then I wanted to just touch a little bit upon the nature of the Emery companion. As I said, the more stringent requirement is that the cloud size needs to be 10 to 11 centimeters. So these naturally can rule out some compact objects such as neutron star and white dwarfs because they're too small to produce the sizes that we need. And also small black hole masses never reach the required cloud size because the influence radius is too small. At the same time, black hole with masses, let's say, beyond 100 solar masses have shorter GW spiral times, and also there is still no evidence that because with 10 to the 3 to 10 to the 4 solar masses even exist, so we didn't want to go there. Then stars can get tidally disrupted, and for at least 2 sources among the 4 that we model, the pericenter is very close to the tidal radius, so there is a question of whether how much the star can survive punching through the disk. Although we've seen some more development in the star model. So what I would argue is that it can be both. It doesn't have to be the same object in all the sources. Furthermore, in 3 out of 4 sources, the star would overfill its Rauschlob for the parameters that we infer from the timing properties. And the stellar radius is independent on the relative velocity, so it will be somehow harder to reproduce different amplitude QPEs, but as I said, so we prefer a black hole companion with mass a few tens of solar masses, but the companion does not have to be the same companion in every source. So we cannot completely rule out stars, of course. So these are the results that we obtained with our model for the two regular sources, GSN and ERO2. So the upper panels are the data that you've seen plenty of times today, and the lower panels are actually our calculations, so they're not fitted. They're just, it's just the results that we obtained plugging in these orbital parameters and essentially evolving the system so that the MRI can precess both upsidally and nodally, although the nodal precession is very long, and the disk can also precess nodally. The disk precession in these two cases is not terribly relevant because it's very long, so it doesn't make a huge effect on the light curve. And these were the sources that were the easiest to reproduce just because of their more regularity. Then Join has talked about more on ERO-QP1, which is one of the less regular QP sources, and which I think shows these 5 days to 6 days modulation in the QPs that we reproduce exactly with the disk precession. So I'm really happy that this has been working out in at least some of the epochs of this source. And then, of course, the hardest one is this monster here, RxJ, that shows flares that are super close in time, and it's very hard to reproduce this without any precession, and especially without the disk precession. And as you can see, we did I would say, fair job, but not a very good job as the previous sources. So this is the hardest, and this source needs to be investigated even further. The other nice property that we get from our model is that, as also Join showed, basically as this ratio, so the QP temperature to the quiescent temperature goes to 1, so the quiescence, the temperature increases, then QPs cease to exist. And this is what we get, so the temperature radius between the final temperature of the cloud and the initial temperature of the gas in the disk. And as you can see, as m dot, so as the accretion rate onto the primary increases, this ratio decreases, and this means that the QPs are not detectable anymore. So this is another, I would say, hint that this might be a reasonable model to explain these QPs. Then, since there are many parameters in our code, we can see what is the effect of varying each one of them, just to understand what sort of modification of the light curve can we expect. So if we increase, this is done just for GSN, which is the most regular one and the one that we reproduce better. So if you increase the black hole spin, you can see that you change the time scale of recurrence, so you change the timing properties along with the amplitude of the QPs. If you increase the eccentricity, you can see that you produce behaviors that are more similar to RxJ. So this suggests that RxJ, indeed, we use a higher eccentricity to reproduce RxJ. So this is another important hint of the orbital parameters that we can constrain. If you assume the MRI to be retrograde, there is no hope to get the high luminosities that we observe. So we can rule retrograde orbits out, at least for this choice of parameters. And then, as I said earlier, for GSN, the disk precession does not matter that much. You can see that you get slightly lower amplitude peaks, but the recurrence time is still there. So now we are looking into, we're simulating impact between a companion and a disk, and a TDE-like disk. And then I'm not sure how to play this. Maybe like this, yes. So we have so far simulated for impacts. So the details of the simulation are just that we So the orbit is takes into account the post-Newtonian term, which we implemented in the code. The disk has both gas and radiation pressure. It's adiabatic, so it's allowed to cool and heat, and we assume that it's just a black body cooling that is cooling the disk. We let the disk relax first, and then we introduce a companion to do the impacts. And so what we eventually want to do is to measure the luminosity of the cloud that is being pushed out. And if you actually look at the simulation edge on, you can see that at every passage, indeed, you have two clouds of material that are expelled on both sides. So the first, I would say, the very preliminary result is that the cloud luminosity is compatible with QPEs, but then still further investigation is required. Now this does not go on anymore. Okay, great. So then the last thing that I want to mention is that, again, on the matter of stars versus black holes. So these are calculations done by a student, a former graduate student, now is a postdoc in Bicocca, and he has developed this very nice Fokker-Planck code to calculate how many MRIs and how many stars can be found in the nuclei of galaxies. And you can see here the number of stellar black holes and the number of stars calculated at 1 parsec. This is 10 to the 6, so 10 to the 6 is here, and you can see that at 10 to the 6, the ratio between the two is more or less 10 to the minus 3, so stellar black holes are less common. But then if you extrapolate this number at 100 RGs, which are the scales relevant for QPEs, then the number density is comparable between the two objects. So yes, so I think I'm done with the time. Okay, I'll just go quickly through the conclusions. So we reproduce somewhat fairly well the behavior of QPE sources, reproducing the light curves using MRI disk impacts. We assume that this to be formed by a tidal disruption event. And the combination of the apsidal and nodal precession frequencies can give you the variety of behaviors, of timing behaviors at least, that the QPE sources have shown. We assume a mechanism that is analogous to the mechanism proposed by Itai and Brian. From our model, we also get the nice feature that the temperature ratios, as the temperature ratios decreases, the QPE disappear, which is seen in the observation. And so I would say that this relationship can work in both ways. So QPEs can help constraining TDEs properties, especially TDE disks properties, and vice versa. And with that, I'm done. I'll thank you again for the attention. I'll take questions.
Alessia, thank you very much. I realized I neglected to introduce you at the beginning,
That's
so
fine. That's totally fine. I mean, it's the last talk.
Exoduce you. Ryan, go ahead.
Thanks for the talk. I guess our concern with the black holes is that their effective cross-section for interacting with disk is basically the Bondi-Hoylton rate. And so in order to get that to be comparable to the size of, say, a solar mass star, the relative speed of the black hole through the disk has to be very low. So you have to require an orbit which is more or less co-rotating with the disk. But then if you're saying, okay, there's precession and the geometry is always changing, I don't see how you could always have that favorable geometry to basically interact with the disk with the same cross-section. So my concern is just that, that for a typical impact parameter, unless you invoke a very massive black hole, but there are other reasons that might be disfavored. So I think that's, that's my argument against it. It's a tiny interaction, but maybe you have.
Yeah. So this puts a stringent constraint on the relative inclination. This is why I'm saying that it's probably, since the number of QPE sources is increasing, then, this is an indication that it might not be as fine-tuned as we assume it is. So we require inclination below 15 degrees, mutual inclination between the disk and the embryo, and this gives you like a few % out of the whole solid angle, because we rule out retrograde orbits as well. And so yeah, I agree with you. But then in our model, the change in the mutual inclination it's taking into account, and so also the change in relative velocity.
So it always stays within 15 degrees.
Yeah.
Okay.
Yes.
Thanks.
Thank you.
Yeah, my question is also kind of related to Brian's. So how is the amplitude of the flare depend on, how is the, actually I didn't quite understand how the amplitude is calculated. Each one you have the peak.
So yeah, so this is exactly what we do.
Oh, it depends on the radius and the temperature.
Yes,
right?
that's
And
correct.
the temperature, can you go back one slide?
Yes, this
the
one.
temperature would given by the jump condition.
This is the Rankine-Hongonian conditions
Yeah,
for shocks.
and then if the relative speed, if you're kind of a grazing, kind of the relative, it may not be supersonic.
No, that's right. That's right. Yes, I agree with you. So this, yeah, you need to be careful about the Mach number here.
I see. So that is something that's close to 1.
Yes.
I see.
Yeah.
Yeah, then the gas is kind of cold to begin with. How does it expand? It should expand at the sound speed, right?
Yes.
Meaning the expansion and the second equation R as a function of T.
Yes.
That should be this. Is that taken to be the sound speed expansion, or?
No, exactly. What we assume is that it expands by a factor 3 within the QPE lifetime.
Oh,
that's it.
And then the QPE life, or the QPE duration.
The QPE, duration. Yes.
And that is prescribed.
And that's yes, the observations. Yes. Okay. It's just to reproduce the light curves.
I understand how.
No, but thank you.
No, I understand. Yes, thank you. Yeah.
Thanks for the nice talk. I guess maybe this is super naive, but does the luminosity of the disk and the luminosity of the QPE depends on the angle, like the observational angle? Because I guess that if you see these bubble puffing up, but the disk is face on, is less.
Yes.
With respect, like the luminosity ratio would be less than if I see it edge on.
Well,
is this stupid or not?
No. No, that's right. We assume the observer to be directly looking at the disk, like from the Z plane, I would say.
Okay, then
so more or less face on.
The second question is, would you be able to constrain the geometry of the system and like how we watch the system based on this?
I don't know. I have to think about it. I wouldn't say it's trivial though.
Maybe one kind of immediate thought about this is if your analysis is accurate enough to account for light travel time effects.
We do include them.
Yeah,
but
I think the timing of the flares will change as a function of this inclination.
Yeah, we do include them, and for the observer looking at the disk, they're not relevant, but then as you incline the disk, or you incline the observer, whatever.
So I think with perfect timing data, you could in principle say something also about the geometry of the system relative to the observer.
Yeah.
I guess kind of maybe related to Brian's question, I think maybe now also with the results we saw today, it's kind of brings into question, maybe we need to kind of brings our heads together and think about the nature of the orbiter. And I just suggest maybe next week we can dedicate some time to kind of a discussion about, IMBHs or stellar black holes versus stars, and kind of see where the kind of constraints are and what can we say about this.
Yeah. That would be great. Yes.
That's so nice. I wanted to prompt this, but you've done it yourself. That's amazing. I didn't want to put you on the spot. Awesome. Actually, my question is about the ton of data that we have for your QP1 now. So we could probably try and fit these 80 bursts, I wonder, do you need to know how many occurred in the gaps, or you don't care about it? Because that's a whole different...
Yeah. So we thought about that, and we not only for EuroQPE one, which would be the ideal candidate since it has so much data now. But yeah, I mean, in order for, and we also did some very preliminary tests with GSN using a nested sampling model to feed the, and so yeah, the problem is encoding the gaps. Like how do you tell what's going on in the gaps? So I'm not sure I have an answer for it, but I'm happy to think about it more. And definitely for Johin's source, I think it would be actually the best thing to do at this point. The only thing, the other thing that I wanted to mention is that for that source specifically, the weird profiles that you see that seem to be the overlap of different QPEs, we actually saw something similar when we looked at the long-based light curve that we reproduce because of the precessions that eventually combine together, and you can have peaks that are close to superimposed with one another.
Can I ask one more question? Okay, yeah, I was going to say, so effectively, the black hole has the advantage that it won't get disrupted. So you can run your code and see all the in the same source, same black hole spin and whatnot, and you see the different behaviors that can be seen. You can try and give us a sense of, you run it for 10 years, I don't care, and then you give us a sense of the phase, the fraction of time that it has spent in a well-behaved state compared to a more complex state. So we can try to use the current data we have and plan for more in a way that makes sense, so we know what gaps to have in our monitoring, what gaps not to have in our monitoring. So because we have been doing things pretty randomly at the moment, I think. And I forgot my other question, so I think
you can ask me later.
Yeah, I forgot.
For questions, please, oh, you have another question?
Sorry, yes. Actually,
I was bait and switch.
So another thing is that since the black hole won't get disrupted, it would be good to know, since you require a fairly low angle, what would happen at different angles? So would you stop seeing QPs for some phases and then recover after a while? I guess the black holes will lose a lot less energy through the collisions, I'm guessing, like in orbital energy.
Yeah.
And so I guess you can just use the precession of the disk as the major change in the relative inclination. And you can give predictions if we see something disappearing, and if it's just due to disk precession in case of a black hole, how long should we wait before asking more time? So we don't, overload XMM since Norbert is here. And I want to make my TOs believable, so if you can give us a little bit of information based on a prediction from the model, that would be great. Yeah, we can chat next week.
Okay, yeah. I don't know what I did.
Guess we're done. Let's thank our speaker, Alessia, once more time. Thank you.